So I know you guys, a lot of you have done the self-study that I asked you to do before this lecture and the one before it. So you should know the relationship between mean arterial pressure and cardiac output and total peripheral resistance. So given that the mean arterial pressure is 102 millimeters of mercury and the CVP is 2 millimeters of mercury, and by the way, if I do not give you the CVP, you may assume it is 0. But if I do give it to you, then I expect you to use that information, and you will need that information for this lecture. It will become apparent why. And the cardiac output is 5 liters per minute. So what is the total peripheral resistance? I heard a 5. Who else? Anybody? I heard a 20. Anybody else? You sure you don't want to just guess them all? Very good. It is a 20. Here's how you calculate it. Ohm's law, delta P, change in pressure equals flow times resistance. 90% of life is showing up. 90% of the rest is Ohm's law. It defines how everything flows, okay? Be it air, water, blood, whatever. Ohm's law is where you want to go. Electrons, it's all the same. For electrons, we use voltage instead of pressure, delta V. And we use current instead of flow, I, but resistance is the same, but it's the same equation, Ohm's law. It defines how things flow. You have a driving force, in this case it's pressure, you have flow, and you have resistance to flow. And they're all accounted for, okay? So delta P is the mean arterial pressure, that is the arterial pressure being generated, say, by the heart in the arteries. And the central venous pressure is the venous pressure that is just about right filling the heart. It's equivalent to the right atrial pressure, okay? So this is the pressure drop across the system as blood flows from high pressure to low pressure, okay? 102 minus 2 equals 5 times the total peripheral resistance. The total peripheral resistance is, of course, the resistance across the entire system. We'll talk about that tomorrow in hemodynamics. And so 100 divided by 5 gives you 20, okay? 20 millimeters of mercury per liter per minute, all right? We will come back to that. I did not ask you to calculate it as an academic exercise. The primary determinant of cardiac output is heart rate, stroke volume, or total peripheral resistance. Very good, heart rate. Heart rate has the highest dynamic range. Stroke volume would be next. Total peripheral resistance has nothing to do with it, okay? Except in that it may change the stroke volume. If you increase the total peripheral resistance, you will increase the afterload. But it is not something that is accounted for in that equation with stroke volume there. You alter stroke volume, you alter heart rate in order to get a defined cardiac output or alter cardiac output. That's how your body works. Okay. Finally, the cardiac output from the right side of the heart is normally greater than the left, less than the left, or the same as the left. Which is it? It's the same. I know it sounds foolish. You would be surprised at how many M2s will, even after this lecture and after the one before and after the heart lectures I did, will try to tell me that the walls are thinner, you generate less pressure, so there must be less output. Not correct. No. They have to be the same. If my right was pumping more than my left, then my lungs would blow up with blood and I'd burst. And I'd do it in relatively short order, okay? Whatever comes out of the right has to be pumped out of the left at steady state, or my blood volume goes up and down, okay? They are normally the same, okay, at steady state. Cardiac output equals heart rate times stroke volume. Cardiac output is the same from both ventricles, and here are our determinants of stroke volume down here. They all come down to end diastolic fiber length. The more you stretch your fibers, the more force of contraction, and therefore the more stroke volume, okay? And that tells you how much is going out of the left side. And of course, whatever's going out of the left side will be returned to the right so that it can go out the right side. So at steady state, all the flows are the same. If your cardiac output is 5 liters per minute, then there's 5 liters per minute being returned via the venous system at steady state, okay? So our venous return is proportional to the pressure gradient divided by the resistance. That is Ohm's law, okay? And we actually do have a pressure gradient between the peripheral venous compartment and the central venous compartment. Now, the central venous compartment is the great vessels of the chest, the pressure in the great vessels of the chest, and the right atrium, okay? And in order for blood to flow into the right atrium, you know that the pressure must be lower in the atrium than it is in the peripheral venous system, otherwise it would not flow, okay? So the central venous pressure will typically be lower than the peripheral venous compartment, and that is why you get flow into the heart, okay? There it is right there, and don't forget Ohm's law, all right? Filling of the ventricle is determined by the pressure, the right ventricle is determined by the pressure in the right atrium, which is determined by the venous pressure, okay? And the more venous pressure, the more the pressure gradient, the more filling you get, and the more filling of the right ventricle you get, and the higher the end diastolic volume in the right ventricle is. And then you should think of everything from the right ventricle to the left atrium as being a passive circuit, for passive conduit for blood. What I mean by that is there are no reflexes, there's no vasoconstriction like there is on the systemic side. There's nothing really regulating that flow. So it's basically just a series of pipes, as far as we're concerned, that flow through the lungs and into the left atrium. The reason that's important is because we typically say that the left ventricular stroke volume is dependent upon the right atrial pressure. And that's because everything in between is passive. Whatever is determining filling on the right side is going to determine filling on the left, okay? There's nothing regulating that flow in between. It's just connecting them by pipes, all right? So when you see right atrial pressure and you see left output, bear in mind that we are assuming that there's a relationship there as if we were saying left atrial pressure, okay?